So there is one thing common between tools like Google Docs, Trello, and Figma that they are all seamlessly collaborative, which means multiple people can work on the same screen and see changes made by each other in real time. So what data structures and algorithms power this interactiveness? When multiple people are editing the same thing in real time, there are bound to be merge conflicts. How are they handled automatically? To discuss this, we have Vipul with us, who is champ when it comes to CRDT, the domain that makes such systems possible. And today we'll pick his brains and explore this super fascinating domain. So let's get started. So over to you, Vipul. Let's start with a brief intro of yours.
Hi Arpit, thanks for the opportunity. I have been a long time reader of your content, so nice to be here. So I am a software engineer. I have worked as a data scientist as well before, and I am really into databases. I worked with database company before, worked as a data engineer as well, and now again working as a data base engineer. We are building a decentralized database. So that is what I have been doing, and we can talk about CRDTs. I would not be able to go a lot into the mathematical depths because it has people say that you need 2 PhDs to understand CRDT paper.
God.
So yeah, but I will try my best.
We'll definitely do our best to pick your brains. Thanks so much for doing this. Okay, so let me start with the most basic question. What are CRDTs and basically where do they help?
So CRDTs were developed around 2011 by a guy named Mark. I am not able to pronounce his last name, so please Google. The premise was collaborative editing tools. So how do you make collaborative editing like Google Doc, for example, more efficient? So there is one assumption in Google Doc that you have to always be connected to the internet in order to edit the document. The reason is that there is a algorithm which is known as operational transformation. So whatever operations you do, it is sent over the internet and it gets resolved into a centralized server. But let's say if I want to build a tool which has to work offline, or a collaborative tool which is more decentralized, where this assumption is not there that there will only be a central server to resolve the conflicts. Because let's say if we both are sitting here in this room, it seems pointless to send the data, in the US servers to get the conflict resolved if we can do it over Wi-Fi. So these were like the initial motivations to develop CRDTs, and the first version of CRDT was introduced in 2011, and primarily CRDTs are data structures, conflict-free replicated data types, and often CRDTs, when you say CRDT, it is clubbed with some algorithms. So data structure alone is not useful here. You have to have some algorithm which will work with this data structure. So that is what CRDT is, like in a very high level introduction.
So then it's like Git, because in Git also you have basically local copies of your repositories and then you do, but in Git you have to resolve the merge conflicts on your own. Here it would be that the conflicts are not even possible, or even if they are, they would be like, let's say, automatically resolved. Like, is my understanding correct?
Yes, Git is a very good example to understand collaborative editing offline. But yeah, as you said, that Git does not resolve conflicts. Git has, you have to individually go and resolve merge conflicts. But let's say if we both are writing some document, then I may not know what you are exactly doing. That's the beauty of programming language, right? If I see the code, I understand what is happening here, but I may not be able to do that when somebody is editing some document or something like that. And the second thing is, Git does the whole job of conflict resolution is extremely mathematically intensive, as well as a lot of time. It takes a lot of time to resolve conflicts. Let's say if you take example of proof of work or any consensus mechanisms, for example, so those types of conflict resolution tools are not possible when you are dealing with Git, right? And most of the time, the conflict resolution in CRDTs also has got some drawback, which I would like to talk about eventually. It's not a perfect tool. to be implemented in Git. But yeah, Git is a good example of collaborative offline editing tool with no automatic conflict resolution.
So to at least start with, obviously it takes 2 PhDs to understand CRDT, but at least to start with, Git could be a good start. Okay.
Yes.
Okay. So you spoke about that CRDTs are a class of data structures in combination with some algorithms. Like if you can shed some light on how, a very simple example of a data structure in combination with some algorithm that would basically power this.
So basically CRDTs, I mean, if you read some papers, they're implemented in two ways. Either you can implement them in sets or lists or trees. So these are standard data structures which are used. But when you talk about what properties the algorithm should have, so there are three properties which the algorithms should ideally provide. One is that is the heart of CRDT, optimistic replication, which means that there has to be eventual consistency. Now, eventual consistency is saying your limit n tends to infinity. You will never reach there. So an eventual consistent system is never consistent because it can only be consistent if there are no updates after a point of time, right? But everybody keeps making updates, right? So let's say we have two databases, yours and mine, and we will continuously keep making updates to the database. So there will never be a point in time where the database will be actually consistent. Like practically not possible, but theoretically it is possible. Let's say if for 1 hour or for 3 hours, both of us decided not to do any commits, then the database is consistent eventually. But yeah, so that is one property of algorithms which CRDT should provide. The other thing is that the algorithm should be able to resolve any inconsistencies or merge conflicts which happens. Now, how do they do it? That's a separate question, but that is one property. The other thing is that the assumption should be there that whatever algorithm you are developing, it has to assume that the nodes will be able to work independently. And sometimes even there is a disconnection between network for a long period of time, it should work. So the partitioning problem in the CAP theorem, CRDT pay a lot of attention to that, to work with partitioning. Whenever your laptop or your server is not connected with internet, it should work even at that point of time. And so these are like the three things which makes any CRDT algorithm work. There are very popular implementations of CRDT like logroot. RGA is one very famous implementation of CRDT. So and there is also a very famous library, AutoMerge, which is written in C++ and JavaScript. It is maintained by Martin Kleppmann, who has written the book Designing Data Intensive Applications. Yeah. So yeah, that is about it. Like if any algorithm follows these assumptions, and if you have trees, lists, set, so those type of data structures with which you can get an algorithm to follow these assumptions, then we will be able to say that your system is a CRDT system, or your implementation is a CRDT implementation.
Pretty cool. Pretty good. And I didn't know basically Martin Kleppmann sir had so much thing to do around CRDT, but that's really fascinating to know. Okay, so what I understand from this is that your CRDT helps you keep a local copy of data. Like each of the system would have a local copy of data, and they might make initial set of changes to that local copy, which then without having a need of a central resolution server per se, you can still just have those two devices exchange. May not be a P2P, maybe a centralized communication still, but you don't need a central conflict resolution server. Right?
Yes.
So this makes it a really good use case for a geographically distributed database, right? Which is what we might see a lot of adoption of CRDTs in tools, maybe like basically Cassandra. I read somewhere, I'm not really sure, but I think Cassandra also uses a flavor of it to basically resolve some conflicts or to not have conflicts at all. But then this gives very nice low latency user experience. Like they think that they are just writing to the local copy while it is automatically behind the scene getting synced across geography. Right? Is this why, is that the main USP of CRDTs when it comes to basically when it comes to the side of databases.
Yeah, I mean, extremely good example. So geo-replication is a very important feature which CRDTs unintentionally provide, because like they were not initially designed to do that, but people figure it out that this can be a brilliant use case. A lot of CDN servers have implemented CRDTs to especially the servers who are like extremely on the edge. A lot of IoT devices have got CRDT implementation because their network is very flaky a lot of times. So they implement CRDTs. Then yes, a lot of databases which claim to be geo-replicated, their CRDT becomes a great use case, because let's say if I have got one server which is in US, one server which is in India, even in India, one is in Delhi, one is in Mumbai, depending on various regions. And let's say I am not able to connect to US server, or even the users are decentralized. I am playing the game and accessing Indian server. You are playing the game accessing US servers. So there, if I start to be consistent, if I start to become ACID compliant at all points of time, it becomes problematic. So I have to like leave the C, which is consistency there, and go towards optimistic replication or eventual consistency.
So which means that the downside of using CRDTs, you will not have strong consistency, but an eventual strong consistency. Right?
Yes. So a lot of like most of the cloud databases are claim only to be strongly consistent, because it is extremely hard to be ACID compliant when you are that distributed and geo-replicated.
Correct, because you cannot have strong consistency across networks, like across basically geographically distributed databases. So yeah, it makes sense to drop C of ACID while basically focusing on others, and that let C be handled by CRDTs.
Yeah, in a way.
In a way. I might be definitely oversimplifying, but yeah.
Yes.
Oh God, nice, interesting. So, with respect to databases, you said that there are a bunch of disadvantages in adoption of CRDTs. And you wanted to talk about the drawbacks. If you could, feel free to add to that.
So, okay, before I go forward, one very open database, very open about they are using CRDTs, React, RIA.
React, which is used by Uber very heavily.
Yes. Yeah. So they one more thing. If you want to implement write through cache, so most of the systems implement write back cache. When you just for the listeners, if your website writes something, it goes to the database, and if it is committed there, the transaction is successful, then only the data comes to the cache. So that's a write back cache. If you want to have a write through cache, when you have a write through cache, you will have extremely fast writes, because cache can be updated very quickly. But how will you make sure that the whatever is there in the cache will get consistent with the database? So in that use case, a CRDT can be a great tool.
That's a great, because that's the most common question in general, which basically people ask me, hey, if I'm writing to the cache, how it gets synced to the database, because there might be another write which is coming and hitting the database while your cache is also accepting the write. So this is like a classic basically split brain problem, where two people are accepting the writes and now they have to do that resolution. Then how do you figure it out? Great. This is really interesting of use. So now it opens up a plethora of applications because of this.
Yep. Now the problems or the drawbacks of the CRDT. So CRDT, it's a common saying that CRDTs are extremely easy to implement badly. Okay. So the reason is that there are few problems which are so I'll tell you how CRDT works. Let's take our names, for example, Vipul and Arpit. We both have added the name at the same spot where the cursor was in the document, and we were offline, and now we both are online, and the merge is happening. So a very simple way to do this is you take so it's a 5-character name, right? Both of our names are 5 character. So the first index will be 0 and the last index will be 1. So 0 is the start of the document and 1 is the last end of the document. And between there are 5 spaces, VIPUL or ARPIT. So I denote all the spaces as rational numbers. So V is 0.2, I is 0.4, and L becomes 0.8. and similarly your name is, but this is there in your own systems. Now, when the merge will happen, since we were there at the same spot, and there is no time, because in distributed system it's extremely hard to manage time. So, what will happen? How will I differentiate your 0.2 with my 0.2? So, what I'll do is I'll take a simple thing that if I am node A, you are node B. So there is a hard code rule that node A takes precedence over node B. Okay. So now the merge might become V A I R P. So, because the numbers are there, right? So interleaving is a big problem in CRDTs. So there has been a lot of work to overcome interleaving. A lot of implementations around collaborative text tools. So collaborative text tools, like if you keep reading the papers around that area, those are the ones which pushes the field of CRDTs the most. So I think there is logsec.
Logsec. It does.
Yes. So logsec uses CRDTs, but they also have interleaving problems sometimes. If you write the document back to front, then CRDT will be completely effed up because it won't be able to resolve conflict. But luckily, nobody writes the document back to front.
Like from the start to
the. So you go to the end of the document and then you write towards the back. So that if you do that, a lot of papers in CRDT will fail to resolve the conflicts. So interleaving is a very big problem in CRDTs. So what a lot of implementations like RGA, for example, RGA is a very good implementation which I think mostly resolves interleaving problem. What they do is they say instead of having this simplistic data structure, let's go with trees. So V is a parent node, I is the child of V, so Vipul, so it's just like a tree. So the entire document is represented as a tree. So when you have that, then this ambiguity is not it's not present at that scale, which is there when you represent the document like a simple rational number set, which I did in the start. So that was one thing. But again, there might be conflicts which can still happen. So there, what they have done is RGA, that they have used vector clocks, or which was introduced by Leslie Lamport. So to resolve the timestamp problem. So you have got trees plus timestamp. Now, since you have got both the things, the interleaving problem gets resolved. However, like they don't claim in the paper that mathematically it will never happen. So there is no proof that it will never happen. It might still happen, but practically we don't observe it that much.
Okay. So that's okay. So it might happen theoretically, but it might happen, but up until now there is no theoretical proof of it. That it would definitely not happen. So,
never happen.
But practically we have not seen it yet. There is like all the data structures that we studied in college now they seem to be in action. Like they are now really overpowered. Like trees, set, and this, and who would have thought that we would solve problems like this? Pretty interesting.
But even if you really want to understand CRDTs, if you understand order theory, so if you understand what a semi-lattice is and these things, then understanding CRDTs become really easy. Because most of the time, a lot of operations. So there is something known as CRDTs are of two types. One is the one is the state-based CRDT and one is CVRDTs. So CVRDTs are convergent replicated. So CVRDT is actually an old term. Now people call it, I think it is known as, so I'm actually getting confused. So basically CRDTs are of two types. One where the entire state is present, and another where actions are present. Okay. So I mean, the name can be whatever, but these are the two distinct types. So a lot. If you really want to understand order theory's perspective of CRDTs, then state-based CRDTs will give you a lot of insights that how order theory from set theory, which is actually like a complicated term, but it is seventh level maths. I am not sure, 7th or 8th sometimes, where we studied sets. So it is like of that level mathematics. But you will be able to understand CRDTs merges much better.
So you are recommending to go for either the operation or the set-based. Which one are you recommending for anyone to start?
So most of the Most of the papers go with state-based CRDTs because replicating entire operation may become challenging at a lot of times, depending of what type of application you have. Let's say if I am doing a database operation and I'm not sending I'm sending all the state, then sending state of the database, entire state of the database at all points in time become very complex. It's much better to send operations that just do these things and you're done. But if you are dealing with a 100 MB file or where, then you can send the entire state, right? Where merge so it depends on the application.
Pretty interesting. There's so much to explore in this domain. So one last thing, like obviously we get something, we lose something. Everything in basically core computer science or software engineering is a trade-off. So if CRDT gives us this strong feature of where we don't really have to deal with the merge conflicts and all, then what it takes back from us?
Performance. Because conflict resolution. So, I mean, there are implementations, even RGA, which I have kept saying for a lot of time. RGA takes up to 5 minutes to resolve a conflict. So if we both are writing a document, assume that every 5 minutes you are getting interrupted because conflict resolution is happening or something like that. So it's not possible to build what CRDT is, aiming to build. They want to build offline collaborative tools. CRDT have got a lot of application in database. It's fine if a database becomes consistent after 5 minutes. Nobody cares. But if you are right, but if you are building a collaborative tool with an end user and the end user is waiting for 5 minutes, that's a problem. But again, I think majorly it is not because of the mathematics or the theoretical aspect of CRDTs. It is because the most popular library, which is AutoMerge, maintained by Martin Kleppmann, that was not written keeping performance in mind.
Okay.
So if you take the library, if you study the library, you can find easy optimizations which you can do. So even that team which maintains this AutoMerge library, those guys are rewriting everything in Rust to be more performance efficient. And there is another library if you just want to get started right off the bat. So YJS is another library maintained by somebody else. I don't remember.
I've heard that about YJS. Yeah, that's pretty cool.
Yeah. So that library is efficient. It may not have all the resolution of problems which is there in the AutoMerge, but it is a quite efficient library.
But then tools like Google Docs exist, and they seem to be quite performant for an end user. Like so then are they doing something different, or are they relaxing some constraints there?
No, they are doing something different. Google Doc does not work offline, as I said, and they use a different class of algorithms known as operational transformations. So whatever you do, all the operations are sent across the server, and you see the end result of the transformations actually.
Okay, so they are not really using CRDTs per se, but they are using operational transformations. So CRDTs are mostly heavily used on the side of databases and not on collaborative tools.
Practically, that is happening because CRDTs, the intention to build CRDT was to do decentralized offline merges. So in tools like Trello, where we both are editing a to-do list, it might create a lot of problem, or it might not be efficient to do that. It is okay if everyone is using, if behind the scenes centralized servers are being used or something like that. But where this constraint cannot be present, the existence of a centralized server to resolve conflicts, their CRDTs are extremely important.
Like database replication.
Yes. Now, but if it's just from my mind, I mean, I have not done a lot of research, so I might be completely wrong here. I am really curious in understanding how CRDTs will work in a BFT scenario.
BFTs?
Byzantine fault tolerance scenario. So where you cannot trust servers. So here the assumption is that all the nodes here which are making changes to the CRDTs are non-malicious. But if the nodes get malicious, then will CRDT work, or because I have not read anywhere in the papers that this is an assumption. So if it is not an assumption, can CRDT handle those things as well?
Which means like building BitTorrent on top of CRDT. You don't trust anyone.
Yes.
You have to basically come up with something that ensures that, hey, even if you're not trusting, still your overall network cannot be taken down.
Yeah. So this example which I gave was also there to establish one difference, which I think beginners fail to understand. CRDTs are not actually replacing consensus. If you build a merge conflict resolution solution with the malicious nodes, I believe CRDT with consensus will have to work. Right.
Yes.
So because conflict resolution or the consistency is different from consensus. But if we come in a non-BFT scenario where things are fine, everybody is non-malicious, the differentiation becomes blurry. That where what is the need of consensus if CRDTs are working or stuff like that.
Pretty interesting. Nice. So one last thing from my end. This was all fab. But if basically someone wants to just get started with CRDT, like any site, any YouTube videos that basically you would recommend?
Yes. So I would recommend I'm not able to recall the video or the blog. So just Google and you will find how CRDTs are implemented with counters, geo-replicated counters. So there are 3 nodes. And every node is incrementing. Only one operation is happening, incrementing a variable. How will you resolve conflicts without consensus? So there are a lot of blogs. It's a standard problem, CRDT problem. It will also help you to understand why you cannot use add operation because commutativity should happen and idempotency should happen. Add operation is not idempotent. If you add something with itself, it becomes twice. So, but max is idempotent. So max of 0 and 0 is still 0. It's not 1, something like that. So you will be able to understand that. And then Martin Klipman has also got a lot of videos around CRDTs. If you take CRDTs, non-academic introduction is the title of the video. That is not by Martin Klipman, it's by somebody else, but very good explanation. And once you have read that, make sure that you watch CRDTs, The Hard Parts by Martin Klipman, where he goes into detail of all the papers and breaks down everything, trees and everything, and tells you that here exact problem exists and here is how we have resolved it and stuff like that. So that is a very good video. This
is quite fascinating. Now it feels like next 2-3 months of my life are sorted. This is so interesting. But thanks so much. Thanks so much for doing this. This was really helpful, really helpful. I loved every bit of it. But thanks so much for shedding light to this. So, anything else as part of your closing remarks? Anything that you'd want to add?
Yeah. So I would just say one thing, that a great thing what Arpit is doing. It's not like he has not asked me to say this. It's just a general thing which I am quoting. That watch his channel and make sure that you become more than somebody who just aims to get placed and things like that. Make sure that you truly understand what engineering is and how beautiful it is. You are basically taking atoms from the power socket and building out brilliant stuff. It's almost like magic. So yeah, try to become asli engineer.
Thank you so much, Vipul. This was quite generous. But thanks. Thank you so much for doing this. It was really insightful. Thanks once again.